You don't have to download an app to access them, nor do you have to keep their batteries charged. But reading can be one of the more painful challenges in a student's daily life. It requires a great deal of mental effort and discipline to read, especially to read challenging text well. What goes into reading, cognitively speaking? How is it possible that we convert a series of visually presented lines into a piece of meaningful information? One major aspect of doing this entails recognition. In this video, we'll discuss the principles that explain how we recognize written text and the best method for increasing our speed and accuracy of that recognition. Recognition, and in this case visual recognition, is a cognitive process whereby we connect perceptions to our stored mental representations. In the previous video, we explored how sensory data is converted into conscious perceptions. However, it's one thing to consciously perceive an object, it's another to recognize that object as something. This distinction between perception and recognition is not easily grasped. Ordinarily, perception and recognition appear to arise simultaneously and instantaneously. Perhaps you might appreciate this distinction when, for example, looking at a text written in a language that you're not familiar with. You perceive the text with no problem. You recognize that there are individual lines, but you're unable to connect the writing to anything meaningful. Your mind lacks the proper mental representations to make such connections. In contrast, if you turn to a text written in a language you do know, the meaning becomes immediately apparent, perhaps even effortless. Not only do you recognize individual words, but you simultaneously process and recognize the individual letters that make up those words. Of course, not all writing in our native language is recognized with the same degree of effortlessness. Several factors influence reading fluency. One of the most important factors in recognizing a word is its frequency of occurrence, or how often you've encountered that word before. High-frequency words, such as the and is, are recognized so effortlessly that our eyes may barely fixate on them while reading. At the other end of the spectrum are infrequent words, such as winsome or intrepid. Even if you have learned the meaning of these words, it's likely that your eyes will fixate on them longer, taking time to connect your perception of the word with your stored mental representation of its meaning. Cognitive scientists are able to experimentally measure this word frequency effect using a lexical decision task. In such a task, participants are presented with a series of words and non-words and asked to determine whether each letter string is a word or not. The aim of this tool is to measure response time. A consistent finding from such research is that infrequent but real words entail a lengthier response time compared to high-frequency words. Increased response times happen not only to words you've been exposed to frequently, but also words that you've been exposed to recently. This is called repetition priming. We'll discuss later on in this video the theorized cognitive mechanism for why word frequency and repetition priming lead to faster recognition. The insights gained from these observations hold major implications for improving reading ability. Most speed reading programs are found to be ineffective, and a major reason for this has to do with a distinction between reading efficiency and reading accuracy. One's reading efficiency, or speed of reading, and one's reading accuracy, or comprehension, are to some degree inversely related. The faster you read, the lower your comprehension becomes. Speed reading techniques can teach you to become a better skimmer and how to make better inferences while skimming, but it's much less effective in helping you understand and recall material that is less familiar, such as what you might find in a textbook. But there is one proven technique shown to improve reading speed without sacrificing comprehension. That one technique is reading more. The more you read, the more you build up the connections between your perception of the words and the mental representations of their meaning. Reading better requires reading more, and as you read more, you develop greater fluency with certain words and topics, allowing you to approach other texts with similar words and topics faster, but while maintaining strong comprehension. This is not the only technique for becoming a better reader, and there are other factors at play for individuals with reading difficulties, such as a reading disorder. However, with all the apps and programs out there aimed to help you become a better reader, it's surprising that so many neglect a basic principle of improving one's reading ability, which is reading more. It's sort of like an individual trying to lose weight by paying money for a trainer and gym membership, but paying no attention to their diet. All that hard work fails to show results if you neglect the most fundamental and influential factor. So why does frequency and recency, or priming, lead to greater reading fluency? To address this question, we'll consider what are called feature nets. If you recall from the videos on perception, the visual system simultaneously processes different features of perceived objects. We spoke about processing features related to color, shape, and motion. But we can be more specific as there are feature detectors that respond to the orientation of lines, such as whether they're vertical or horizontal. You may also recall the concept of binding through neural synchrony. In the case of perceiving and recognizing letters, distinct functional groups of neurons responsible for responding to certain kinds of line orientations when activated simultaneously register as unified objects that can then be recognized. So for example, if a group sensitive to vertical lines fires at the same time as a group sensitive to horizontal lines, you may get a pattern of brain activation that calls forth a mental representation of the letter L. How quickly these detectors fire to a particular stimulus and how quickly the distinct pattern of activations are bound together and interpreted as one object depends upon those two factors already mentioned, frequency and recency. A word presented frequently or recently has, in a sense, revved the engines of specific feature detectors, so they're more sensitive to that information when it's presented again. In other words, feature detectors have a lower response threshold and a generally higher activation level for a word presented frequently or recently. Another important aspect of word recognition is that we recognize letters and words better when they're presented within an understandable context. You may think that information is easier to process when there's less of it, but this is not the case. Just as it's more difficult to understand a person without considering their cultural and family background, it's more difficult for the mind to recognize individual bits of information when disconnected from any meaningful context or situation. Let's take letters, for example. What letter is this? Is it an H or an A? Well, it depends, and it takes longer for the mind to come to a decision here than if that same information is presented in the context of the following words. Here, the mind doesn't hesitate in identifying what each letter is. The context of an entire word makes an individual letter more easily recognized. This is known as the word superiority effect. An explanation for why this happens can be found in the parallel distributed processing model proposed by McClellan and Rumelhart. According to this model, the mind not only simultaneously processes the features of sensory inputs, but the feature detectors influence each other to become more or less likely to fire. So, for example, when the feature detectors responsible for the letter T are activated, this feature detector excites other feature detectors that are commonly paired with the letter T, such as maybe an H or an A, but inhibits other feature detectors rarely, if ever, paired with this letter, at least in the English language, such as X and Z, making those detectors have a lower activation level and a higher threshold to fire. These excitatory and inhibitory connections help to explain the word superiority effect. I'm more likely to recognize a letter in the context of a word because the surrounding letters support the firing of detectors associated with any individual letter, so long as it's within a familiar string of letters. You won't find the word superiority effect from a rare letter string such as T, X, Y, E. And that's because they don't have the same connections among feature detectors that would facilitate them recognizing individual letters as quickly. How does this help with reading? When reading, you are continuously making sense of word phrases. Just like individual letters, you're more likely to understand individual words and word phrases when they're read within a larger context. However, in this case, the larger context may be the topic or theme associated with the text. When the overarching topic is clearly understood, the mind can more quickly read and accurately process the information provided by individual words and word phrases. This is one of the major reasons why it's recommended, especially for dense and technical material, to survey the text before reading it. This initial work prepares the mind to understand its content by situating it within an understood context. This requires a more active reading approach than may be typically employed by most students. By surveying the text first, various feature detectors are primed and more ready to activate when presented with the individual bits of information within the text. Of course, sometimes it's difficult to grasp the overarching topic through surveying if you have had little exposure to the topic in general. Your ability to form a mental representation of the overall text is limited, and so your ability to understand its content will also be limited. This is a perfectly normal part of the learning process for the novice, and it's why, returning to this video's earlier theme, it's so important to read more. The more you read, the more you build up mental representations. Reading more will also help you build up those feature detectors to more readily fire and to form an intricate web of interconnected detectors that assist each other in recognizing that material when it's encountered again in another text. And as you'll do this, you'll find yourself one day turning back to a text you thought was impossible and wonder to yourself how you could have ever considered this material to be so difficult to read in the first place. What is it about faces that exerts this power over us? Why do they seem to hold a unique place in our perceptual experience? To begin, it would be helpful to consider how we recognize most objects. If you recall in the previous video, we used feature detectors to recognize letters and words. However, one issue we didn't address is how we recognize variations of the same object. For example, I can recognize a chair from multiple angles, and I can recognize many different kinds of chairs despite a wide variety of designs. It's highly likely that when presented with a chair that has a design I've never seen before, that I'll still quickly recognize that object as a chair. This is only one kind of recognition of taking a specific case and identifying it as belonging to a general category. There are other kinds of recognition. Another kind that identifies a unique object, not belonging to any larger category. When I head out to the parking lot after shopping and I search for my car, I'm not trying to recognize a car in general. I'm looking for my car, and there is only one object in this parking lot that can meet that criteria. In this situation, I'm not looking for those features my car has in common with other cars, but rather features that no other car has, such as the license plate, the particular scratches on my bumper, the object hung on my rearview mirror. These two forms of recognition are in fact quite different from a cognitive perspective. Let's first consider how we recognize objects as belonging to a general category. Look at this image, and what do you see? Do you see a cat? Most likely. And if so, what made you come to that conclusion? What about this image of a cat is essential for considering it to be a cat? You would probably focus on particular features, such as its ears, nose, whiskers, and tail. In other words, there are some essential features that need to be present for you to recognize an object. This is the central idea behind the recognition by components, or RBC model. The RBC model, like the feature detection models previously discussed, analyze objects in terms of their basic shapes and arrangements. These basic shapes in RBC model are what are called geometric ions, or geons for short. They serve as the basic building blocks for object recognition. These geons can be combined in a number of ways and are displayed in a defined pattern for specific kinds of objects. By requiring only a limited number of essential geons rather than to perceive the entire object, this allows us to recognize objects despite the angle we're seeing the object from. So whether I see the cat in front, on the side, or behind, I can still easily recognize the cat as a cat. This ability to recognize an object independent of any particular angle is what we call the viewpoint independent recognition. However, as mentioned, this is not the only kind of recognition. There is also the recognition of unique objects whose identity cannot be subsumed in some general category. One notable case is the individual human face. In contrast to ordinary objects, we are quite sensitive to variations of a person's face and can be thrown off when looking at a face from certain angles. This is what is called viewpoint-dependent recognition. One notable piece of evidence for distinguishing between objects and faces is found from a class of neurological deficits. Agnosia is a loss of the ability to recognize objects. There may be a difficulty in recognizing an object after having processed and assembled its features in the mind, as in the case of associative agnosia, or there may be difficulty in assembling the individual features in a recognizable manner, as in the case of apperceptive agnosia. You can assess the difference between these two kinds of agnosias using a relatively simple test. Present a client with a line drawing of an object, such as a key, and then ask them what do they see. Individual with associative agnosia will not be able to say what they see. In other words, they won't recognize the depicted object. However, ask them to copy the object on a blank piece of paper, and they'll have no difficulty in doing this despite still not recognizing what they're drawing. Now imagine another client, this time with apperceptive agnosia, and they're presented with a similar task. They also will not be able to name what they see. However, if you ask them to copy the object, like you did to the first client, they will have some notable difficulty in reproducing it, perhaps drawing its features in a disorganized manner. But if you ask that same client to draw a key from memory without any drawing of it present, they'll be able to perform this task. A couple of observations here. First, we can see the difference between perceiving features of objects and organizing those features into a whole. Second, we can see the difference between a recognition problem and a memory problem. Agnosia is not a difficulty in memory. It's a difficulty in connecting perception with a stored mental representation that's previously formed by memory. There's another kind of agnosia distinct from the two mentioned called prosopagnosia, which is the inability to recognize individual human faces, even faces of people you know well, even your own face. Prosopagnosia can occur in the absence of the other agnosias mentioned. This term combines the words agnosia, which means without knowledge, agnosia, and the word prosopon, meaning mask, face, or person. It's with this condition of prosopagnosia we find a strong piece of evidence for the uniqueness of human faces from a cognitive perspective. Whereas damage to the what or ventral pathway can produce a visual agnosia, it is damage specifically to the fusiform gyrus of the temporal lobe, or what is called the fusiform face area, that is associated with prosopagnosia. Faces are special not only because there's a distinct brain region dedicated to them, but also because we seem to process faces differently than ordinary objects. Rather than analyzing its individual features, such as the geons mentioned before, we appear to process faces holistically. It's the face's overall configuration, the spacing of the eyes, the height of the forehead, the length of the nose, etc., that provides the necessary information to recognize someone. Even slight changes in the relation of these features can lead us to have trouble recognizing someone. This helps to explain the composite effect. Individuals asked to identify the top half of a face will have much more difficulty doing so when the bottom half is aligned that belongs to someone else's face. When the bottom half is removed, it then becomes easier to recognize who the individual is by just viewing the top half. This is because minds are inclined to process faces holistically. And so it's difficult for us to dissociate the top half from the bottom half unless the bottom half is removed for us. There remains debate here, as the fusiform gyrus may not solely be dedicated to processing faces. However, the uniqueness of processing faces has some support from an evolutionary perspective, given that our capacity for socializing is one of the unique elements of our species and seems to have been essential for survival of our ancestors who were otherwise pretty physically weak compared to many other animals. It would have made sense that we're especially attuned to the most socially relevant nonverbal information we encounter, and that is the face. Whatever cognitive neuroscience may end up showing with regards to the uniqueness of face perception and recognition, there can be little doubt about the power faces have over us. Thank you for watching. Please feel free to like this video, and if you want to see more, subscribe to this channel. I'll see you next time.